How's it going, everybody? My name is Little-Simpson, and today I'm going to be talking to you guys about the stochastic process. We're going to be going over some different variations of it, examples of those variations, and of course, we're going to start with the origin of it. So, stochastic itself as a word means randomly determined, so we could also say that the stochastic process is known as a random process. The word stochastic itself comes from the Greek word for stochastikos, literally translating into aim at guess, and stakos is the prefix of it, which literally means aim. The history of it is fairly recent, or at least modern probability theory is. It started in about 1933. The person that made major contributions on this in the 40s was Joseph Doob. So now that we have the history and the origin of the stochastic process out of the way, we can get into the formalities. First, we're going to start with a formal definition, and the definition of a stochastic process is a collection of random variables that yield percentages over a period of time. The differences in the stochastic processes is that some are discrete and some are continuous, and we'll get into that in a bit. And the main thing to understand is that percentages yield probabilities. So now that we know where the stochastic process comes from and the formal definition of it, let's dig a little bit deeper into it, starting with random variables. Before we learn how to use random variables in the stochastic process let's talk a bit about random variables themselves. This may be new to some of you, this may be a review. The formal definition of a random variable is a variable taken on numerical values determined by the outcome of a random phenomenon. A random phenomenon should not be taken as a spooky term, since it just means something that may or may not happen in the future. Another important thing to know is that the probability distribution of a random variable x, they are all associated with each x value. A probability distribution is simply going to be a method for finding a probability. And the simplified version of this is saying that any time or score we choose is going to be associated with a probability. So as mentioned before, now that we're done talking about random variables, it's time to get into the different forms the stochastic process can take. We're going to start with a discrete stochastic process. In other words, we're going to be using discrete time steps. So before we talk about discrete time steps, we're going to talk about what a discrete random variable is. And they're basically the same thing. The definition of it is a countable and usually finite set of variables over a period of time. 1, 2, 3, 4 is an example of that. Imagine 1, 2, 3, and 4 is our x0, x1, x2, and x3. Things to note is that the probability of each x value is between 0 and 1. That's because we're talking about either 0% or 100%. And anything in between is also fair game. The other notable thing is that all x values have a sum probability of 1 or 100 because the probability of anything happening is 100%. So now we finally get to talk about how these random variables and the stochastic process is used in sports. So first of all, when it comes to sports and the stochastic process, what we're doing is we are finding a probability of one team or one player winning during the game. This process usually isn't used at the beginning of a game. And the first one we're going to talk about is discrete time steps in sports. So basically what we're doing is we are taking random variables, or in this case what we're talking about are holes, balls, shots, rallies. And what these are they're countable and very finite. For golf, for example, when you look at holes, there's 18 holes. And you get one score for each of those holes. That is a finite set, and you can count them. So, other examples of sports that use discrete random time steps are going to be cricket, snooker, and tennis. If you know anything about snooker, other than that the blue ball is worth 5 points, you know more than me. Congratulations. So now that we know how a stochastic process is used in a discrete way and the sports it's associated with, let's do a quick example. So in order to find an example of a discrete random variable, we're going to stick with our golf, and we're going to be talking about Tiger Woods. He's a very famous golfer. So he's on hole 4, and right now he has shot a 2, a 3, and a 4 on the first 3 holes. So he's gotten a birdie, a par, and a bogey. What we want to do is find the probability that he shoots a 3 on hole 4. We can see our distribution down below, and what that is that's a binomial distribution. And plugging things into our equation, we're going to define P as the probability of him shooting a 3. He did it 1 out of 3 times, so 1/3. Q is going to be 1 minus P, or the probability that he does not shoot a 3, which was 2 out of 3 times, so 2/3. X is going to be the number of times that he shot a 3, or 1. And N is the number of trials, or in this case, the number of holes the Tiger has already shot at. In this case, 3. So when talking about the solution, we're going to start with the N given X, and that's just talking about choosing, where you're choosing one thing given 3 things. You have 3 options there. Then we're going to talk about the other parts, which is going to be the probability the Tiger shot a 3, which was 1/3, raised to the number of times he shot a 3, which was 1. Next, we're going to talk about the probability that he did not shoot a 3, which is 2/3, raised to the number of times that he did not shoot a 3, which is going to be 2. That 3 and the 1/3 to the 1 cancels out very nicely, so you basically have 2/3 squared, and you get 44.4%, which is going to be the probability that Tiger shoots a 3 on hole 4. So now that we're finished with that example of a discrete time step, now we're going to go on and look at a continuous stochastic process. So continuous time steps, or continuous random variables, is going to be infinite random variables over time t, such that t is greater than 0. And what that means is we can't have negative time, so at any point in time during a game, what is the probability of X happening? We use a density curve to find probabilities, and a density curve is a range of events that is found by taking the area under the curve. Again, all of the X values are going to have a sum probability of 1 because the chance of everything happening is 100%. So continuous time steps in sports are used by generating sequences, and those sequences are things like goals scored, the change in leaders, the baskets scored, and these are done usually over an uncountable period of time. Sports this is used in is things like football or American football, hockey, athletics, speed skating, and basketball. And again, just like before, now that we're done talking about how a continuous stochastic process works and what sports it can be used in, let's go through an example. The example we're going to be using is going to be a basketball game between the Boston Celtics and the New York Knicks. I have shaded out the 4th quarter so that we can look at the first 3 quarters of the game. What we're going to do is predict what the score will be, or at least in this case, who the winner will be. The first thing to notice about this chart is that each line has an equation with it. That meaning that the Celtics, the green line have an equation with the number of points over time, and the Knicks in the blue have. So for the sake of time, what we're going to be doing is we're going to be finding the area under the curve, and the team with the largest area is going to be declared the predicted winner. How we do this is we have to find the equation of either those green or blue lines, and this can either be an exact equation or it could simply be a best fit line. We're going to use that equation as f of x, and we're going to take an integral to evaluate that from 0 minutes to 48 minutes, or 3/4 of basketball. So again, for the sake of time, let's assume that our equation is simply x. We're going to be taking an integral, which is going to be finding the antiderivatives. So what we're going to do is basically use the power rule, where we're going to add a power of 1 to x, so we have x squared, and divide it by that new power. So we have x squared over 2. We're going to evaluate that from 0 to 48. What that means is we're going to plug in 0 and 48 for x, and then find the difference between them. When we do find the difference between them, we find out that the area under the curve is 1,152. So using Desmos, we can get a visual of what this area under the curve looks like. That shaded in blue area is our 1,152 units. That thick blue line at the hypotenuse of the triangle, if we want to call it that, and the black line coming out of that is our original equation. That can also be associated with either of the Knicks or the Celtics score at that time. Once again, for the sake of time, and this time when I say the sake of time, I mean me not learning the entire Greek alphabet, we're going to skip the proof because it's long and tedious of the process itself, and we're going to skip right ahead to an unanswered question, or a question that at least I have that I don't understand completely yet. So the question I chose to consider, which is very simple on the outside but very complicated on the inside, is there a way to calculate mixing time? What is mixing time? Well, variation distance mixing time, which is a more complicated way of saying it, is the smallest time t such that the total variation distance of a probability measure is small. In other words, what's the smallest time in which probability differences in the future are negligible? In other words, if we were to take our basketball scenario, the probability of the Celtics winning, let's say, does the Celtics winning percentage stay the same relatively from 45 minutes on, from 50 minutes on, from 55 minutes on? Well, that's a very complicated answer, especially with how sports is so unpredictable. And with that, we're going to wrap things up. The sources I used really quickly: Boundless Statistics were what I used for the definitions for random variables in the stochastic process. ESPN was what I used for finding the charts for the Celtics and Knicks. Symbolab was what I used for the photos of the integral and the steps taken to solve that integral. Desmos was taken for using the image of the area under the curve, and Wikipedia was used for the definition of mixing time. Once again, for the sake of time, and this time when I say the sake of time, I mean me not learning the entire Greek alphabet, we're going to skip the proof because it's long and tedious of the process itself, and we're going to skip right ahead to an unanswered question, or a question that at least I have that I don't understand completely yet.